This video is about transforming graphs of sine and cosine. As always, be sure to start by reading through the textbook and taking careful notes, but now consider the following highlights for this topic. Let's begin by recalling from our previous lesson that graphs of sine and cosine parent functions, as we've called them, or parent or the basic functions, have several properties, and we developed these in detail. If you want to go rewatch those, that'd be fine, but the basic idea is that sine has a period of 2 pi, which means it starts at the origin 0, 0, and then as you move to the right, it goes up and then down and then back to 0 in this snake-like periodic wave function pattern within 2 pi. So that's how long it takes horizontally to do one full period of the graph. And we also notice the same period for cosine. However, cosine, when you start at 0 on the horizontal axis, begins at the top of its wave at 0, 1, and then it goes down and then back up again to that top of the next wave at 2 pi or within 2 pi. And so we developed those in detail in our previous lesson. If you'd like, review those for more on that. Next, we will consider transformations of these basic parent functions. And you may recall this topic from algebra, where you would have done transformations for some basic algebraic functions. It's the same idea, except now we're dealing with these trig functions. So to transform means to change, right? And so we might be shifting the graph left or right or up or down. We may be stretching or shrinking it or reflecting it. There's various transformations we might do. And for these trig functions, we're going to use the following format. Now, this is not the only way to represent these, and so certainly you may find other representations in various textbooks, but I'm choosing to use the letters A, B, C, and D in the following way just to stay simple with it. So we'll take our basic transformation formulas to be the following. For sine, we could say y equals A times the sine of B times x minus c, and then plus d. Now, the way that the brackets or parentheses are interacting, especially in the middle, are important, so carefully study these. If I could read it that way more carefully, it'd be y equals A times the sine of, open bracket, B, open parenthesis, x minus c, close parenthesis, close bracket, plus d. Okay, but it's a little bit tedious to read it and say it that way. Nonetheless, until you are clear with where all those symbols are, it might be good to be thorough in that way. Or cosine would be the exact same thing, except with cosine. So the A, B, C, and D are all in the same places, just dealing with cosine instead. Okay, so what do all these letters mean, and how do they possibly transform the graph? That's where we're going next with this. Well, first there's something called amplitude. And amplitude is equal to the absolute value of A, this letter A that we're using. And I'm using all capital letters for A, B, C, and D. But again, that's just kind of my take on representing this. You could do it with various different letters. So the absolute value of that capital A that's in the front of each of those transformation formulas, that represents the amplitude. Now we'll see what that actually does or looks like soon. And then there's also something called the transformed period. Which is equal to the parent function period divided by b. So note carefully, b is one of the letters in our transformation formula. It's the letter that I've written inside the brackets but factored out of the parentheses, and that's the case for sine or cosine. And then also recall that for sine or cosine, the parent function period is 2 pi, as developed in our previous lesson. So that parent function period will change depending on what the function is. For sine and cosine, 2 pi it is. So for those, 2 pi over b is going to be this transformed period. Now remember, the period is the amount of space, or you could say horizontal time, it takes to go through one period of the graph. As we illustrated with sine and cosine, it's 2 pi. Okay, next, as we think through these transformations, we'll have what's called phase shift. And phase shift is equal to this letter C, this capital C, that's in each case after the x. So it's maybe inside the parentheses, you could say, after the x. And interestingly, it's subtracted in both basic transformation formulas. So it's x minus c. That doesn't mean c is always negative. That means that's the way the formula is written. And this produces a horizontal translation. That means a shift left or right, horizontally. And then we have what's called a vertical translation. So perhaps you could say shift and translation are interchangeable as words to describe what's going on here, but you may see it written this way, vertical translation. That's what the letter D does. And you'll notice that just kind of hanging out on its own with each transformation formula. Now it's written in the way I've done it at the end of each, though there's this plus D at the end. That doesn't mean it's always at the end. You could actually throw it in front, in which case it would be like a D plus, the sine or the cosine. But nonetheless, D does a vertical translation, which could be considered a vertical shift as well. Now that seems like a lot, and it is, but with practice and with a process, I think you'll find that it's really not that bad to be able to account for all of these transformations in a particular graph. So let's now review the steps for graphing two periods of a trig function with transformations. Now when we developed sine and cosine graphs in the previous lesson, I graphed one period, but then demonstrated or showed from the animation that you could easily extend that to two periods. The point is that periods just keep repeating the same shape over the same interval. And so, graphing two isn't that much more difficult than graphing one, but just for practice, we're going to be graphing two here. And the following steps can help, especially if you recall from maybe some algebra that transformations do have a certain order of operations that matters. And so we want to make sure we're accounting for that. These steps should do that for us. Sometimes people, start rigidly to memorize steps. That's fine if you'd like to do that. But I think just practicing with them over and over again will probably make them familiar enough so that you won't have to worry about just a rote memorization, but more just practicing the process. All right, so the following 7 steps can get this done for us. First, if any value is in front of the x variable, and to be fair, I should say it doesn't always have to be an x. The main thing is that the input variable, and that maybe that could be written as a t or a theta or some other variable used, but maybe in normal beginning context it'll be the letter x. It's the input or the domain variable. Well, if any value is in front of the x variable inside the trig function, and by inside I mean if you go back to our transformation formulas for sine and cosine, you can see the set of parentheses that has the x inside. So we're talking about something like that, but you may or may not see it in this final form at first. And that's what these steps are meant to do. So if any value is in front of the x inside the trig function, factor it out of the entire input as b. Okay, so that's what you can actually see done in the transformation formulas above here for sine and cosine. The letter b is factored out in front of the parentheses. So it's written that way in these formulas on purpose because that's our goal, but you don't always see it written that way when you're given a problem, as we'll see. Okay, that's step 1. Step 2, if b is negative, this value that you've now perhaps factored out, We use the negative identities. Now this is in a previous lesson. You can go back and review those. It's about whether the functions are odd or even. Okay, so we'll get into that with some examples shortly. And then thirdly, determine the transformed period and label two periods on the x-axis. Well, that's what we described here briefly above. This transformed period, this is the 2 pi over b. It's like a little formula for it. Of course, 2 pi is relevant for sine and cosine. With other functions, as you'll see, that will be different. But for sine and cosine, we're going to use that little formula for the transformed period. And then label two periods on the x-axis. This really isn't that bad. It's a matter of just counting by the certain fractions we have for our special arcs. Then we'll plot the x-intercepts, and this is all based on the unit circle values, as you'll see. So we'll be recalling a lot of that. Fifthly, we'll plot the min or max values using the amplitude, including any vertical reflection if a is negative. So remember, a was this leading coefficient variable out in the front of the sine or cosine for the transformation formula. And if that value is negative, of course, that would result in a vertical reflection, as we'll see. Next, we will shift points using C. So this is where we called, for C, we called that a phase shift or horizontal translation. So that, or a vertical translation, which shifts up or down, that will be next. And then we'll simply graph using the parent function shape and direction as a guide. So in other words, after we get through step 6 here, we'll have a set of points on our graph that are spaced out and moved over in the correct way. Then we'll have to rely on what our parent function looks like to know what the shape should look like, which, as you'll see, is not that bad as long as we refer back to those basic parent functions for sine and cosine as we have them reviewed above. So, okay, that seems like a lot, and it is. But as I said, as you get using these steps, I think you'll find it's not that bad, and once you get used to this process, it can move much more quickly. So let's go through several examples. Our first is going to be this: f of x equals negative 2/3 times the cosine of x. We want to graph the function over two periods. All right, so we're going to run through our steps above, and the first step says that if any value is in front of the x, then factor it out. Well, you'll notice in this case, it's just cosine of x. There's nothing in front of the x, and you would actually see something there for what I'm talking about. So in this case, there's nothing to do for step 1. Okay, step 2, if b is negative, well, that's the value that we would have just factored out in step 1, and we didn't do anything there. So we don't have a negative b, which means we skip step 2 as well. Okay, and again, you'll see those steps happening in future examples here. For step 3, determine the transformed period and label two periods on the x-axis. Well, in this case, the transformed period, that's the 2 pi over b. But really, you could say in this case that b is 1. So the period isn't any different. It's just 2 pi over 1, which is 2 pi. So there's really no change to the basic or parent function period for cosine in this case, which means, fine, we'll stick with it as 2 pi. And then we want to plot or label our x-axis with two periods. So we're going to go now to an actual graph that we have nice and elongated on the x-axis. We discussed at the end of the last lesson that really t and x can be used interchangeably at first, but then we shift over to using x for the horizontal axis, so I'm going to stick with that for now. You could say f of x or y for your vertical axis. And we want to graph two periods on this x-axis. Well, if one period is 2 pi, then two of those periods will be 2 times that, which is, of course, 4 pi. Now, what you may recall from when we developed the graph of sine or cosine in our previous lesson is that all you need to do is start cutting stuff in half. And you do that every time, which makes it kind of a routine and simpler process. So if I'm going from 0 at the origin all the way out to 4 pi for 2 periods, I'm going to start by cutting that in half. Visually, I'll just kind of mark somewhere in the middle of those. course, halfway between 0 and 4 pi would be 2 pi, so we'll mark that down. We'll cut those two new segments in half as well. So halfway between 0 and 2 pi would be 1 pi, which we will mark. Again, visually just kind of estimate where halfway is and put a mark for pi there. Halfway between 2 pi and 4 pi would be, well, 3 pi. And so you can see so far we're just counting by pi's, 1 pi, 2 pi, 3 pi, 4 pi. But we probably should put a little bit more down. So let's cut these in half again. And so between 0 and pi, I'll mark about halfway there. Of course, halfway between 0 and 1 pi would be 1/2 pi, or in other words, pi over 2. And then halfway between 1 pi and 2 pi would be 1.5 pi, or also known as 3 pi over 2. Halfway between 2 pi and 3 pi. So now you can start to see where this was going, except now we're venturing beyond one period, which means we may not be in as familiar territory in terms of like the special fractions we've already been working with on the unit circle. So you can remember that we're just counting by fractions here, right? This is now counting by halves. So it's 1/2 pi, and then 1, and then 1.5, and then 2. So next would be 2.5, and then you can just kind of convert these over to some fractions, right? So 2.5, if you think of that as 2 and 1/2, just convert it to an improper fraction. 2 times 2 is 4, plus 1 is 5 over 2. So this is really 5 pi over 2, just using some fractions. Then 6 pi over 2 would be 3 pi. And then 7 pi over 2 would be next. And then 8 pi over 2 would be 4 pi. And sure enough, that's 2 full periods. So again, the counting by fractions thing is a good kind of backup to resort to if you just feel uncomfortable with extending beyond what we have in one full wrap of the unit circle. You're just extending the same pattern, the same intervals further. All right, now that gives us a bit to work with. Is it enough to work with? I don't know. When we originally graphed the sine and cosine functions in the previous lesson, we cut even these in half again. So let's back up to our steps to make sure we're following this basic step process to graph the full picture here and see if we have enough for it. You'll recall in our steps above that we want to get to the place where we can plot the x-intercepts in what I've called step 4. And actually, we've done all the way through step 3 at this point, so that's where we are. Which means we need to figure out, do we have enough on our axes, or our axis, to plot all the x-intercepts for cosine. Now, these intercepts are, at first, for the parent function, and of course we'll be translating possibly in some of these functions to move them over. But if we go back to the cosine function, or you refer back to where we started or finished in our previous lesson when we graphed it, you'll notice that the x-intercepts occur at two places in the first period of cosine from what we saw in the previous graph. And if you go back and review, such as maybe the unit circle diagram we have in previous lessons, or the graphs we wrote or drew previously where we had more markings on them, you'll find that the cosine value is equal to 0 when the input value is pi over 2. That's the first time it hits 0. And then it also hits 0 at 3 pi over 2. And so really those are the two x-intercepts within one period of our cosine graph. Now, if we look at what we have marked so far in trying to go for 2 periods, pi over 2 is on there. So we'll mark a point there for our first x-intercept. And then so is 3 pi over 2. So we'll mark that. Now, you can thankfully keep this pattern going. That's kind of the point of a periodic function. The next time we would hit an x-intercept would be 5 pi over 2, and then 7 pi over 2. Now, how am I getting those? Well, you could do it two ways. Number one, you can just keep counting around the unit circle in a positive counterclockwise direction. As we've done in previous lessons, you can count around as many times as you need, and you'll keep hitting the same places, right? Cosine is 0 when the x-coordinate of the terminal point is 0. Well, that happens at the top or the bottom of the unit circle. You can spot it there, or you can start to just notice the pattern. Like every other tick mark, the way I've drawn them so far, is where we're seeing these x-intercepts. This is the process that helps us just use the pattern to our advantage for these periodic functions. And so that'll do it for the intercept. Let's go back up and just keep an eye on where we are with these steps, right? We just did the intercepts. That was step 4. Step 5 is to plot the min or max values using amplitude, including a vertical reflection if a is less than 0, or in other words, a is negative. Well, notice that in our example that we're working on, a, which is the value out in front of our function, this is negative 2/3, which is obviously negative, so this matters, and this means there's a reflection. So we'll call this vertical reflection. It's not hard to do, you just have to flip vertically the graph upside down. And then, of course, to get the amplitude, we can get that from the fact that a is negative 2/3. We'll say it this way: the absolute value of a would be positive 2/3. In other words, our amplitude is 2/3. Okay, so what do those two things mean? Well, we have to recall that a vertical reflection means we're flipping the graph over vertically. We'll do that in a second. The amplitude means that instead of going up as high and low as the parent or basic function does, which would be like a 1 and a -1, right, typically, we would be multiplying those high and low values by 2/3. That's what the amplitude means. So instead of going all the way up to 1, that means we're going to go only as high as 2/3. And similarly, only as low as -2/3 because of that amplitude. So you could imagine then it kind of shrinks the graph vertically. Now, where does the cosine function start? Well, typically the parent function or the basic function for cosine, as we have graphed here above, starts up at the point 0, 1, right? Well, we're going to be flipping this graph upside down because of our vertical reflection. So instead of starting up at 0, 1, we're going to start at the bottom of the graph, and that's going to be now at 0, -2/3. It would be -1, but remember, our amplitude means we multiply that value by 2/3, which means it's actually -2/3 instead of -1. So our first point is going to be at 0, -2/3. We know already that we have an x-intercept at pi/2. We marked that already. Now we can start to follow the pattern of the sine function. We know it's a wave. If it starts low, as we've already said, it's going to start curving upward through this x-intercept at pi/2, which means it's probably going to hit its highest or its max at pi, which would be at the value or at the elevation of 2/3. And so once you get that first little piece going, the rest just kind of falls together because the pattern continues. You can put in the rest of your low points. You know, your next low point is going to be at 2 pi, just following the pattern. Your next high point is going to be at 3 pi. Again, low point, I mean -2/3 vertically. High point is positive 2/3 vertically. And then it's going to finish at the bottom, the low point, all the way where x is 4 pi. So if you follow this pattern and just kind of draw a snake-like curve connecting these points, you get, well, the graph of our function, accounting for the -2/3 that was in front of it. How did we? Well, because the negative meant vertical reflection, and the vertical reflection, I should probably label on this I'll color coordinate. So that means we flipped the graph upside down vertically. So instead of starting at the top like the parent function would normally, we started at the bottom at the point 0, -2/3. And then once we have the bottoms and the tops, the mins and the maxes, the valleys and the peaks, so whatever you want to call those, all plotted just in a periodic, repeating pattern, we just connected them to draw our graph. And there it is. And again, since our amplitude was 2/3, we multiplied those values that were normally 1 by 2/3, and that's why we're getting the positive or -2/3 as our highest and lowest points. So we've accounted for our transformations in this graph. Okay, let's go on to another example. This next one begins as f of x equals, and then it's written as 4 minus 2 sine of x. Now you'll notice a couple things in this one. Number one, there's a 4 at the beginning and then a minus 2 sine of x. It seems like it's a little bit strangely ordered, perhaps you could say. I mean, it's fine to do it this way. It's not strange, but it is different than we have our transformations formulas written above. So what I'm going to suggest on this one is that just to be clear and matching them up to what we have above, I'm going to rewrite this as negative 2 sine of x plus 4. So I'm just kind of rearranging where that 4 is. Why would I do that? Because now it matches what we have above. We have an a value in front as negative 2, and then we have a d value at the end as plus 4. Now it still was a d value the way it was written with the 4 at the front, but it can be easy to miss that or get confused about what's what. A here is negative 2, not 4. That's clear to pick up quickly here. All right, so let's go through our steps above. Again, we have all these steps written and we'll just continue to follow through them. Step 1 says if any value is in front of the x, we should factor it out to get the b value. Well, in this case, there's nothing in front of the x. There was something in front of the sine, there was something on its own with the 4 there, but there's nothing in front of the x, which means you could say here that b is 1, just like it was in that previous example. And if that's the case, then we know our period for this function, and this is a sine function, so it'll always be 2 pi over b. In this case, it's 2 pi over 1, so it's just 2 pi, which means there's no change to the period for the sine function. That's what we know it to be. So we start with that, if you can see that above, as step 1. Step 2 says if b is negative, then we use the negative identity. Well, it's not. Step 3, determine the transform period and label 2 periods on the axis. Well, we just determined the transform period. It's really no different. It's just 2 pi. I want to label 2 periods on the axis, so just like we did with the last one, if the period's 2 pi, 2 of them would be 4 pi, and so we'll mark all of our places just like before. Start by cutting stuff in half. So halfway between 0 and 4 pi would be 2 pi. We'll mark that in the middle somewhere. And we'll cut those places now in half again. So halfway between 0 and 2 pi would be 1 pi. And halfway between 2 pi and 4 pi would be 3 pi. And we'll cut those in half one more time, just like we did before. So halfway between 0 and pi would be pi over 2. Now you can just kind of follow the counting pattern by halves. So it's 1 half, 2 halves, which is 1. Next would be 3 halves, or 3 pi over 2. And we're just kind of off to the races counting, right? 4 halves is 2, then it'd be 5 halves. So 5 pi over 2. 6 pi over 2 is 3, then 7 pi over 2, and then 8 pi over 2, which is really 4 pi, which means that's 2 full periods. Okay, so there's our axes labeled. That's a key step in our process. And again, with more practice, this process will get more familiar. Next, we want to actually plot our x-intercepts. So this relies on us understanding what the basic parent function graph looks like. Now we're working with a sine function here. So let's recall that sine has the sine value is 0. If you go back to the unit circle, you can find that all the y coordinates of our terminal points are 0, starting at 0. So it starts at the origin. It's back to 0 at pi, and then 2 pi, which would be one full wrap around the circle. Okay, and then 3 pi would be, again, the other side of the circle again, and then back to 4 pi. So you can start to see the pattern here showing up. If these values, again, are not familiar, go back and review the unit circle. We're just getting everything directly from it. But we're starting by just getting those x-intercepts from where the sine values on the unit circle are 0. All right, so that takes care of step 4, plotting the x-intercepts. Step 5 is going to be to plot the min and max values using the amplitude and any vertical reflection. Well, in this function, let's recall here, for number 2 that our a value is actually now -2. Once we rearrange the function a little bit, a is in front here, it's -2, which means the absolute value of a is +2. Now, since a is negative, that means there is going to be a vertical reflection, and then the amplitude, of course, will be 2, which will stretch our graph vertically a little bit taller and then lower than it was in the parent function. So let's start plotting some things here. If sine typically starts at the origin and goes upward, but we're reflecting it, we have to flip it over. This time it's going to go downward. So we would expect then for halfway between those two intercepts to have a valley or a lowest point where we're at pi/2 for the input. Now, what is that lowest point? Well, again, our amplitude is 2, so the sine function typically goes as low as -1, but we'd have to multiply that by 2, our amplitude, which means it's going to go down to -2. Now, if you could imagine starting to trace what this graph should look like, this wave function, you'd start at 0, 0. Of course, you'd be going downward, right, because we reflected upside down here, and then you'd be going back up to the next intercept and so on. We're not actually going to draw it yet, but I want to put in the rest or some other points just for frame of reference here. So I'm going to go vertically. The next max, or the first max value we'd hit would be at 3 pi/2, and we know that that max value would be 2 because of the amplitude again being 2. We'd multiply the normal max of 1 by 2 to get 2. So we would normally be snaking through these points. I'm not actually going to draw the graph yet because we have more to do. So I'm going to start by just finishing the rest of the min and max points. The next min, if I follow the pattern, I can see the next ones at 5 pi/2, we hit a minimum, and then we would hit the next maximum at 7 pi/2. Again, just kind of following the pattern. You can almost see the graph there, but we're not going to draw it yet because there's more to do. What else is there to do? Well, let's not forget that we also have to increase or translate this graph up 4 units because of the d value as the +4. Everything's got to shift up. It's a vertical translation going up, or a vertical shift. So we're going to do that with all of our points before we draw the graph, okay? And that's really all that's going to happen. Now that's going to mess up our scale a little bit, so I'm going to have to be careful here and see if I can fit it all in, but you can see how every point has to move up 4 units. I'm just going to kind of mark, it's going to be a little bit above the graph, but that's okay. I'm going to put a 4 just to move things up and have enough space. I'll have to clean this up a little bit. I'm going to move my vertical reflection note to be above where A was, just so I can have some room to work here. And then what I want to do is now shift every point up 4 units. So I'll kind of note this with some, I guess, annotation here. We had a point at 0, 0. That's going to be now shifted up all the way 4 units, which would be at the point 0, 4. Okay, but every point is doing this. So the next point we had, which was at pi/2, -2, that's going to shift up 4 units as well. But again, the good news is it's the same amount each time, so you can just imagine everything shifting up 4 units. Just make sure that it's spatially looking okay enough on your graph. The next value, the next point, which was an intercept at pi,0, that's now going to be at pi,4 because everything's going up 4. And I'll just kind of mark the rest of those as we go. Now the next value is going to be even higher. So this was at 2, so that's going to be way off my graph grid. That's okay. It's going to be way up at 6. Vertically, we have to kind of keep everything moving up 4. And so this point that was at 3 pi/2, 2, now it's going to be 3 pi/2, 6. So way up high. And then you can see how this goes from here, right? The next value was at 2 pi, 0. That's going to be 2 pi, 4 now. Everything is just moving up 4. I'll kind of note this here, which is some squiggly movement. arrows to see where things are going. Every point that we had is moving up 4. And this will continue all the way down through the rest of the graph. I'll just kind of draw on the rest of the points here. It gets jumbled into where I was writing, but it's okay. We'll make use of that the best we can. The point is this whole graph has shifted up 4. So then the last thing to do is draw the parent function shape with these adjustments in place. So let's do this, and I'll use a darker color to kind of do this. We know since it's reflected vertically, we're going to start at this point and then being a sine function go downward and then just snake through all of these new points that we have plotted where we have them. And this shows you the full transformation function given everything here, which was a vertical flip, a amplitude change of 2, and then a shifting up 4. Alright, let me just clean this up a little bit so it's maybe a little bit more readable, so I'm not running into my graph. Move some of our notes over. So we had said that A was -2, and this produced a vertical reflection. Of course, we already accounted for that and did it. And what you can see in this gray line now snaking through is the final transformed graph. Alright, let's do some more to see some more variety here. Our next function is given as f of x equals 1/2 cosine of 4x. Okay, so again, refer back to our steps that we'll follow each time. If any value is in front of the x variable inside the trig function, factor it out of the entire input as b. Well, guess what? We finally have something there to do. In this case, you'll notice that there's a 4 in front of the x. Now, in this case, there's actually nothing after the x, which means there's not a lot of factoring to do. There isn't really any factoring to do here. As you'll see, sometimes you have something after the x and you have to factor the 4 like out of the whole thing. This one's even simpler. All we can do is say, well, from what we see here, b equals 4. With that being the case, we have to get the period of this function, which is adjusted based on that. Period for a cosine or a sine is 2 pi, and so we divide that original or basic function period by b. So 2 pi over b, in this case, means 2 pi over 4, which really means pi over 2. If you reduce the 2 over 4, it's really 1/2, so pi over 2 it is. Now that's the period. Of course, if b is negative, we use the negative identity, but it's not. Okay, so we didn't have to do anything for that step. Alright, so we want to get this graphed on our axis, and we want to do it so that we put 2 full periods on there. Now you'll notice 1 full period is now pi over 2. That's a bit different. We've been using the basic period of 2 pi, and now we're kind of scrunching that down. The process is no different though. That's the nice thing. If the period's pi over 2, and I want 2 periods marked on here, what is 2 times pi over 2? Well, it's pi, exactly, right? You can just think in terms of arithmetic or fractions on that. So 2 full periods out would be pi for this one, and you may start to notice this familiar process where we just start cutting stuff in half. Now we're working with maybe some different values because of the adjusted period, but that's okay, it's still the same process. So I'm going to go between 0 at the origin and pi and say, well, half of that would be pi over 2. And I'm going to cut those intervals in half again. Well, half of pi over 2, so between 0 and pi over 2, we'd have pi over 4. Then you can just start counting by fractions if you want, right? 1/4, 2/4, 3/4, so 3 pi over 4, and then 4/4, which is the pi value at the end. Now remember, this is actually accounting for 2 periods because we have an adjusted period from that value of 4 that was in front of the x. It's doing a change to the horizontal stretching or shrinking of this graph, okay? But just simply changing the period with this little formula takes care of it. We don't have to worry about anything else. Now, to be clear, let's cut these in half one more time as we've been doing, just to make sure we have enough on our graph to get the intercepts and the highs and the lows. That's really what we're going for. So halfway between 0 and pi over 4 would be, well, what's 1/2 of pi over 4? It'd be pi over 8. Just multiplying pi over 4 by 1/2. Now you can think of it as counting by eighths. 1/8, 2/8, 3/8 would be next, so 3 pi over 8, 4/8, which is 1/2, 5/8, so 5 pi over 8, 6/8, which is 3 pi over 4, 7/8, or 7 pi over 8, and 8/8, which of course is pi. And it's easy to be thinking in terms of the original period of the function, like, oh, we don't have enough, the period's a full 2 pi. Well, no, remember, we've adjusted it already. So what we're showing is a full 2 periods because one period is only pi over 2 this time. And so this should give us enough space to work with. Now what we want to do next is find the intercepts according to our steps above. And so you'll remember that in this case we're working with cosine. The first time cosine is 0, of course, is way up at pi over 2 in the normal function. But this is where I think it might be helpful sometimes just to recall the basic parent graph. So I'm just going to do a little sketch up in the corner, like kind of up in the cloud here for a second, just to remind us of what we're working with. I think this helps a lot. So the parent function for cosine starts at the top of the hill, goes down, and then back up at the top of the hill within one period, as we saw when we developed that graph. So what we now know is that our graph has to look like that within one period. So that means we're going to be starting at the top. Okay, so for us, for our new graph, the top, wherever that might be, is going to be where this graph starts. We'll put a point up there. The amplitude will tell us how high that is. Now for this graph, the a value in front is 1/2. Of course, the absolute value of a is still 1/2 because that's still positive, which means instead of going all the way up to 1, it's going to go up to 1/2. But as you can then see from the parent function that we've sketched in our minds, to make sure we're familiar with this, one full period goes from high to low to high. So let's do this here. One full period for us is pi over 2. We have that marked halfway through since we're doing 2 periods, which means we have to get back up to the highest point there, and we hit the lowest point halfway between it. So I'm going to put those points in. What are they? Well, again, one full period is 0 to pi over 2, so that means I'm back up to the top of my graph there, which happens to be a vertical level of 1/2, given our amplitude. Halfway between the 0 and pi over 2, halfway between our period, we have the lowest point, which will be now pi over 4, and then this will be negative 1/2, since, again, we're multiplying the amplitude values by 1/2 from the original parent function. So then, if I then use the pattern, notice the x-intercepts are simply halfway in between all of that. So I can jump right to that and say there must be an x-intercept at pi over 8 and 3 pi over 8, and then you can just keep the pattern going by marking the intercepts and the continual peaks and valleys according to the pattern. Once you get the pattern going, it just kind of keeps rolling. You'll notice then at this point there's no shifting left or right because there was no c value that we had to factor out. There was no, b value that we factored out. There's no c value shifting anything left or right. There's no d value shifting any points up or down. All we have here is an amplitude change, which we've accounted for because we've multiplied vertically by 1/2, and a period change, which we've accounted for as well by just computing our new period of pi over 2. Which means we can simply now connect all of our points with a wave-like, snake-like pattern to meet what our cosine function should look like. Okay, let's move on to our next example. This number 4 says f of x equals 4 sine of negative 2x. And so we're going to follow all of our same steps. I'll start moving maybe a little more quickly now that we're seeing the hang of this. The steps just keep repeating every time. In this case, notice several things. This time we have a negative 2 in front of the x. That's a reason to use our negative identities. So let me recall here, negative identity. And for sine, f of negative x, I should say this in terms of sine. So sine of negative x equals negative sine of x, because it's a negative, or it's an odd function. So we did that back in a previous lesson. The negative pops out in front because it's an odd function. And so, in other words, since we have a negative sign in front of the 2 in this one, we're just going to rewrite this using a negative identity. So I'm going to write this as negative 4 sine of 2x. Okay, so that's using the negative identity as stated in our steps above to follow. Once we do that, notice again, like the previous one, there's a number in front of the x. This time it's a 2. And so we would normally want to try to factor that out of anything else, but there's nothing after the x to factor it out from, so there's not a whole lot of factoring to do in this one. What we can say simply by looking at this function now is that a is negative 4. I'm going to put this over on the side. A is negative 4, which means, of course, that the absolute value of a is 4. That's going to affect our amplitude. And the fact that a is negative means we have a vertical reflection. So we'll make sure to account for that as well. And the fact that there's a 2, the b value is 2. There's nothing to factor it out from, but it's still b. So we would say the period is 2 pi over b. In this case, b is 2. Which means the period is just pi. Okay, remember, period is 2 pi over b. B is 2. 2 pi over 2 is pi. So the period's pi. If we're going for 2 full periods, we want to go all the way out to 2 pi. Cut everything in half, so halfway between those would be 1 pi. Halfway between those would be pi over 2. And so 1 pi over 2, 2 pi over 2, 3 pi over 2. We're just counting by halves here. And then we'll cut those in half one more time to, again, make sure we're accounting for enough of what we'd like to see, which would be intercepts and then peaks and valleys. So, of course, halfway between 0 and pi over 2 would be pi over 4. So we got 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, and 7/4. Just counting by fourths all the way up. Like we did last time, let's also just recall what the parent function looks like here. You'll get the hang of this being useful. And so again, if we're just thinking the basic parent function for sine, it's going to go up and then down and then back to 0 within one full period of the graph. Now notice in this parent function here that we actually end up within one period with 3 x-intercepts. There's one in the middle. Not only the ends, the beginning and the end, but right in the middle, there's another x-intercept. So, okay, that matters for how we're going to be graphing these intercepts on our axis here. So we're going to have one right at 0, that's where the function starts. And then the next one is going to, well, before we get to the next one, let's go to the last one within one full period. Again, our period's pi, so we know what that will have another intercept. What this parent function little sketch is suggesting is that we have another intercept in between those to get a total of 3 of them within one period. Okay, so good to know. Now, recalling this basic parent function shape does a lot of help with that. Between all those intercepts, notice that's where we're going to find the peaks in the valley, or the peak in the valley, the highest and lowest point. So between the first 2 intercepts, we would have normally the highest point, and then between the next intercept, the lowest point. However, we have a vertical reflection on this, so let's see. Pick on pink here for vertical reflection. Because of that, we're going to be shifting those to the opposite directions. Okay, I'm not going to leave those pink marks on there, but you can kind of get the idea. that we have to reflect things vertical. We have to flip the graph over. That doesn't mean the intercepts move, it means the peaks and valleys move. So now we're going to be just moving those to the opposite sides. Once we do that, we can just keep this pattern going. You'll notice we've accounted for the b value being 2. Now we've accounted for the a value being -4. As long as we mark our highest and lowest points here, we're at +4 and -4 vertically. And then you can kind of spot the pattern and just keep it going. So our intercepts would be at 0, pi over 2, pi, 3 pi over 2, and then 2 pi. You can just kind of count equal numbers of spaces there to mark those. And then similarly, the pattern will continue with the maximum and minimum, and those will continue to follow the pattern they would need for a snake-like, wave-like periodic graph to account for our period of 2 pi and get 2 full periods on the graph. Alright, let's keep on rolling. Our next example is as follows. It begins as f of x equals -3 sine of pi x. Okay, so we're seeing some things jazzing up this one where there's a -3 in front and there's a pi in front of the x. Let's just kind of do our usual things here, and let's note that a is -3. That means a vertical reflection because it's negative. And then, of course, the absolute value of a would be just 3, so we have an amplitude of 3. Let's also note that in this case, b, let's see where I can throw this, b in this case is pi, which means our period is, for sine, it's the normal period of 2 pi over b. Well, that's pi for this one, so 2 pi over pi, which really just means 2. So our period's just 2. Okay, so we're going out 2 periods. That means we're going to go all the way out to 4. We'll mark that down. Okay, now we're just using integers. This is easy. Halfway between 0 and 4 is 2. Now it's super easy. Halfway between 0 and 2 is 1. We'll cut those halfway places, and then even go maybe one more. Set halfway. You can use either 1.5 or just 3 over 2. Either way is fine. Kind of used to 3 over 2 when we use pi's, but either way is okay. We'll just use the decimals here, I guess. So 1.5, 2, 2.5, 3, 3.5, 4. Alright, so those are our values for the x scale. We also want to recall here that, notice we don't have to use a negative identity for sine because the b value here is positive pi. So we can just leave it as is there. Let's recall the parent shape to know what this thing's looking like. For sine, sine starts at the origin, and the parent function goes up and down and then back up, which means it has 3 x-intercepts within one period, as we just recalled in the previous example. That's just kind of getting the basic shape understood from the parent function. We want to get the x-intercepts plotted here. We know that one period is 2, and for sine we have 3 x-intercepts within that first period, so we'll plot those at 0, 1, and 2. Now this one, this graph has a vertical reflection, and so again, like the previous one, sine normally starts going upward and then downward and so on, but our vertical reflection is going to go the opposite way now, so we'll start downward, which means there will be a minimum value at 1/2 and a maximum value at 1.5, or 3/2 there. And what are those min-max values? Well, if our amplitude is 3, then the highest we go is 3, the lowest we go is -3. And so we can just kind of keep this pattern going. If we keep the intercepts going and the high and low values going, we should be able to fill all the points in and connect them to get a nice wave-like, snake-like graph. Alright, let's roll on to our next example. This time for number 6, we say this: f of x equals 2 times the sine of And then in parentheses after the sign, we have 2/3 x minus pi over 6. Our first step will be to factor out the b value that we're seeing in front of the x. Now this time we have something even after it, the minus pi over 6, which means there is some factoring to do. So let me write this out as 2 times the sine of, I'm going to use brackets after it just to kind of mark this here, and then we're going to factor out the 2/3 that's in front of the x from what else is inside these original parentheses. So imagine distributing the 2/3 in here to get this original input. There'd be an x and then a minus, and then this can be a little tricky to figure out sometimes when you have fractions. So the question is 2/3 times what would give us pi over 6, right? And if that's not a simple value, or especially if it's fractions sometimes, you might need a little bit of a sideshow on that. So sometimes I like to write it out over here and say like, okay, 2/3 times a, I'll just pick on some other letter, has to equal pi over 6. So what is that a? Well, you can just solve for it algebraically. If I multiply both sides of this little simple equation by 3/2, I get 3 pi over 12, which is really just pi over 4. Okay, so a little sideshow here to figure out what this number is, because remember, you're saying 2/3 times what will give me this pi over 6, and if that's not an obvious easy answer, just make up a problem to figure it out. 2/3 times a equals pi over 6, and solve for a. Turns out pi over 4 it is. So that's going to be the value in there, and that little side step I think helps to get that down easily. All right, so now we have the format we want. Let's note a couple things. First of all, we know that a is 2. Now it's positive 2, so there's no vertical reflection here. And that'll change the amplitude, of course, by multiplying by 2. Now we have a b value of 2/3, the value we factored out, and that means our period is 2 pi over b, which is 2/3. Okay, so this means 2 pi over 2/3, flip the 2/3 over and multiply, so that would be 2 pi times 3, which is really 6 pi over 2, which means our period is really 3 pi. 6 pi over 2. Okay, so period is 3 pi. That helps to know as well. Let's see what else. We have now this time, if you go back to the way our original transformation formula was listed, now we actually have a c value. We haven't had one of these yet. But now we can say c equals this pi over 4. We can color coordinate this similarly. So c is pi over 4, that the value we worked so hard to figure out a little bit earlier. That's going to be our phase shift, which we haven't seen yet, but that's okay. We'll see it here without too much problem, I think. And that's everything we'll have and I think we'll need. Now let's go to the axis and mark down same kind of process here. We want 2 periods. If one period is 3 pi, that means 2 of them will be 6 pi. So we'll kind of go out and stretch out the furthest we need. We'll start cutting stuff in half. So halfway between 0 and 6 pi would be 3 pi. Now it gets a little uglier when they're not multiples of 2 to cut in half, but it's okay, not terrible. Half of 3 pi, just think of 3 over 2, right? It'd be 3 pi over 2. So that's like counting by 1.5. So 1.5, and then 3, 1.5 more would after that be 4.5 pi. Think of 4 and 1/2, and converting it over, it'd be 9 pi over 2. And then 6 pi at the end, which you could say is 12 halves. So you're counting by 3 halves, right? 3 halves, 6 halves, 9 halves, 12 halves. That's all that's going on here. and then we're reducing the ones that we can reduce. As we've been doing, let's cut all this in half one more time to make sure we have enough of our special places going on. So halfway between 0 and 3 pi over 2, you'll see all you got to do is get really the first one going, and you can kind of just count by fractions from there. So like cut this in half by multiplying 3 pi over 2 by half, by 1/2. That means 3 pi over 4, right? Just kind of using basic arithmetic there. So we have 3 pi over 4. Now we're just counting by 3/4. So 3/4, 6/4, which is really 3/2. So 3/4, 6/4, 9/4. You can kind of start to catch the pattern here. 12/4, well, that's 3 pi. 15/4 would be next, so 15 pi over 4. After that, we have 18/4, also known as 9 pi over 2. And then 21/4, so 21 pi over 4. And then 24/4, which of course is 6 pi. Okay, so the fractions can get a little ugly, but if you just kind of keep the arithmetic in mind, it's not too bad. Let's again recall that we're working with a sine function, and so we can imagine what its parent would look like. The sine function, again, in its most basic form, starts at the origin, goes up, down, and then back up again within one period. It has 3 x-intercepts, so let's start to mark the intercepts first. As you'll see, we do have some shifting to do, but that's okay. We'll account for that in a second. The intercepts would be at the origin, so 0, 0, and then at the end of the full period. So for us, a full period is 3 pi, which means we'll have one there, and then right in between we'll have another intercept. And so that accounts for the 3 intercepts within one full period. Now, what's going on otherwise? Well, in this case, there's no vertical reflection because the a value is positive, positive 2. So we would expect it to go up and then down and then back up, just like the normal parent function shape. There's no flipping here. So that's good news. That means there's going to be a max in between the first 2 x-intercepts and a min in between the second 2. I'm going to mark those in there, and I'll even mark their vertical elevation, given that the amplitude is 2. So it normally goes as high as 1 and as low as -1. We're going to be going as high as 2 and as low as -2 because of that amplitude of 2. And instead of drawing now the curve in, which could be tempting to do, let's do a couple things. Knowing that we have a phase shift here, I'm just going to keep the intercepts going. So just follow the pattern, every other tick mark. And then keep the max and min pattern going as well. And kind of just keep the wave-like high, low kind of pattern going. Then, instead of actually drawing the graph, which you could at this point, we're not done. I got to do the phase shift, which means we want each of these points. This is phase shift. Each point is going to move pi over 4. The question is which way? Well, if it's a minus pi over 4, as you see in our function after we did the factoring, the opposite of this sign is the way you go, the direction you go, given the transformation formula above. So we're going to go right pi over 4. Now, what that means is that each of these points is going to shift to the right by pi over 4. You may say, well, how far is that? Notice it's not one of our tick marks. The smallest span of tick marks we have on our graph is 3 pi over 4. That's from 0 to the first tick mark. We want even just a portion of that. So what we're going to do is just go ahead and mark in there some extra tick marks a little bit to the right of each of the tick marks that we have, each one of them, a little bit to the right, and every point is going to move that much over to the right. So what we'll do is, let me pick on a different color to illustrate where these are moving. So all these points that we have, the intercepts and the highs and the lows, are all now moving pi over 4 to the right, and that's easily accomplished by simply using the extra tick marks we've drawn in and moving, shifting or sliding every point we have, whether it's an intercept or a max or a min, high or low, shift everything over to the right by pi over 4. After that, finally, I think we've done everything. We've done our amplitude, we did our period change with the b value, we did our phase shift. We're ready to connect now all these final points that we have as carefully as possible with just a wave-like, snake-like pattern, and now we can see it. Now, I wouldn't require you to go through and relabel all these final places. Like when we did the little shift to the right by pi over 4, we have all these new little tick marks in there. It's kind of a math headache to go and relabel all of those. I mean, you can do it, it's not terrible. Like if you're just adding 1/4 to each of them, which is all you're doing really, then pi would be the first one. You know, instead of 9/4 for the second one, or the third one rather, you can just keep adding pi over 4, or just kind of mark the first one, and then I'll get the picture. That you can mark where those are. Now you can verify your first maximum is at the point pi comma 2. That should be consistent with where this graph is. All right, let's move on to our next one. Number 7 is given as f of x equals 1 plus the cosine of 3x plus 2 pi. Okay, so immediately you can see a lot of stuff going on. We'll just pick it apart one little piece at a time. Notice that the 1 is written in front, but you could just as well put a plus 1 at the end. That would refer to the d value that we have in our little formula above, so I'll just call this the d. 1 is the d value. So we'll see that happen. That's just a vertical shift when we get there. Let's start with the b stuff though. So notice we can do some factoring in here. So let's do this. I'm going to rewrite this whole thing then as the cosine. I'll put the 1 at the end here. The cosine of, I'm going to factor out whatever's in front of the x. So that happens to be a 3, which means inside we'd have an x and then a plus and then something else. So the question is, if I distribute the 3 into this blank, what should be there so I end up with pi over 2? All right, like we did before, let's just do a little bit of a side project to figure out what that number is. What we know is that 3 times some mystery number, a, has to equal the value we need to end up there with, which is pi over 2. So if I distribute this 3 in there, what value there, where I'm calling it a, should be there so that I get pi over 2 as the result? Well, you could solve for a here by dividing by 3 on both sides, and it would turn out there that a would be pi over 6 if you divide both sides by 3. So what that means is pi over 6 goes in there as our c value, really. Which means we know enough to get rolling with this one, so let's do that. Notice in this case, oh, I should also say there's a plus 1 at the end. Let's not forget. That's our d value. Okay, so in this case, we have a equals 1. That's kind of good. That means no amplitude change, no vertical reflection, so nothing to do there. B is what we factored out. That's the 3. So in this case, our period is 2 pi over 3. Okay, so some ugliness to that fraction, but we'll be able to handle it, I think. That's the normal period of this cosine function over b. So there we go. Let's see what else. We know that c, in this case, is pi over 6, because it's x minus c there, which we figured out. And then d, of course, is 1, which means we have to shift everything up 1 at the end. Okay, that's everything we need. Let's get to work. We want to put 2 periods on here, and 1 period is 2 pi over 3. So that means 2 periods will be 2 times that, which if you just kind of think of multiplying the numerator by 2, 2 times 2 pi is 4 pi, so that's 4 pi over 3. For 2 full periods, if I cut that in half, same process as always, right? Cut it in half, that means multiply by 1/2. So 4 over 3 times 1/2 would be 4 over 6, which is also reduced to 2 pi over 3. That's cutting that in half. We'll cut those in half each again. So same kind of arithmetic here. 2 pi over 3, think of it as 2/3 times 1/2 would be 2/6. 2/6 is really 1/3, so we got pi over 3. So now we're just counting by thirds, right? One from 0, we got 1/3, 2/3. Next would be 3/3, which is also known as 1 or pi, and then 4/3. So that's enough, except we'll probably need to cut it in half one more time to get the same kind of markings and pattern that we've been used to. We cut it in half a few times, right? So let's do this. Cutting from 0 to pi over 3, cutting that in half, multiply by 1/2, would be pi over 6. Now we're just counting by 6. So 1/6, 2/6, 3/6, which would be pi over 2, 4/6, 2 pi over 3, 5/6, 5 pi over 6, 6/6, which is 1, 7/6, which is unreducible, and 8/6, which is, sure enough, 4 pi over 3. So you hopefully get now the pattern where you just start cutting stuff in half and then counting by the interval of that first span from 0, which tells you exactly how long it is, and then you're just counting by fractions each way. Now, there's a lot going on in this one. So we have several things. We have a phase shift. We have the period change we've already dealt with. That's already accounted for. And then we have a vertical translation as well. Let's recall what the parent function for cosine looks like, just so we're in the right universe here. And this parent function, as you'll recall from previous examples and the previous lesson, parent function for cosine starts high and then dips low and then ends high within one basic period for the parent function, which means it actually has two intercepts within that one period, and then it has a valley in the middle. So let's kind of translate this onto our graph, meaning like copy it on there in that way. So one full period for us is 2 pi over 3, which means that's going to be where we'd have a high spot. If we start high, we end there high, and in the middle between those, so if you count 1, 2, 3, 4 spaces, second one in, the low spot would be down there, and that means we have intercepts in between. So if we use, let's see, I'm going to use some different colors. I'm going to keep the intercepts orange, and our high and low spots will be in between those, as marked here. It's all about patterns, okay? And we'll keep the, speaking of that, keep the pattern going for the intercepts. You'd have another one, so 5 pi over 6 and 7 pi over 6, and then kind of snaking in the same pattern, you'd have your high and low, peak and valley points as well. So now this gives us a framework to work with. Now notice in our function that in front of the pi over 6 we have a plus sign, and in consistent ways that we've seen here we go the opposite direction. So this means we're going to go left pi over 6 for each point. That's a phase shift. We're going left pi over 6. So that thankfully is the span of one of our tick marks. In fact, the way we've drawn it now, every tick mark is pi over 6. So we're going left one full tick mark with every single point. Then we're also going up 1. So we'll kind of do both of these things before we finish here. We're going d equals 1, that means up 1. So we're left pi over 6, up 1. Let's do both of those things and see what happens. If you go, first of all, left pi over 6, then every point is going to move that far to the left. You could even extend in the negative zone here for negative pi over 6. It's too cluttered up there. And then every single point is moving left pi over 6. So I'll kind of draw that on here just for visual sake. Okay, get the idea. I'll just kind of sketch in the rest of them here. And so every original point is moving that far to the left. But then they're all going up 1 unit. Now we haven't even done a whole lot with our scale vertically yet. So let's go back there. So now every point that was shifted left we're also going to then move up 1 unit for its final resting place. Now, also note that we've scaled this already with a 1 and a -1. We're going to have to move higher to account for moving up 1. If you're already at 1, you go up 1 and end up at 2. So we'll have to extend vertically here. But every light blue point that we've already shifted left is now going to be moving up 1 unit to its final resting place. And as you can tell, these can get a little messy, so there's not always a way around that. Just try to be careful. You have colored pencils to use to distinguish some things. That's not a bad idea. You can start to get the idea here, though. So if we connect now all these final points, of course the last one, or would be one way over on the left side up in my picture that's kind of in the way, but you connect all these final pink points and end up with a periodic function translated for cosine as shown. So that's about as messy and crazy as the transformation graphs get. And yeah, it's a little scary if you look at the end result without following each step. So might not be a bad idea to kind of go back and review or rewatch step by step if needed. But that's about as ugly as it gets. So let's do another one, but this one, not as ugly, but it does have one little twist or variation that I want to make sure we see. This one's given as f of x equals the cosine of pi over 2 minus x. So what I mean is if you look inside the parentheses, there's not a whole lot going on with this function, but it seems like it's like maybe out of order inside there. So what we're going to do is just carefully rewrite this to be the cosine of negative x plus pi over 2, which is equivalent to the way it was given, just kind of reordered. So the x is first. It's a little more familiar according to our transformation formula. But then notice there is something in front of the x that would need to be factored out. So then we would say, well, okay, fine. Cosine of, we would take a negative sign out, and that would leave us with x minus pi over 2, just by simply factoring out a negative from both of those terms, the -1 being the value in front of the x as part of our steps above for doing this. Then also recall that given the negative identity for cosine, which is an even function, this negative is going to disappear because the cosine of negative something is equal to the positive cosine of the positive something. Or in other words, cosine of negative x is equal to cosine of x. It's an even function. Just note this right here. This is an even function. So this negative sign vanishes because there's nothing in front. If it's an even sign, you can review that from the odd and even properties we talked about in a previous lesson for cosine, it being even. All right, so really, this is all we're working with here. Cosine of x minus pi over 2. After that, all that kind of moving around, it actually simplified it quite a bit. So b is 1. Well, let's see. A is 1. B is 1. That's good news. That's good news. We do have a c value here. There's no factoring to do, but c is pi over 2. And since it was, in this case, a minus pi over 2, that means we go right pi over 2 because of the minus. And then d is 0. There's nothing to do at the end. There's no up or down movement for this. So actually, it's not that bad. Let's get our graph going, our axis going, and see what we can do. So our period is going to be 2 pi over b, which is 1, so just 2 pi. If we want 2 periods, we'll go out to 4 pi and start cutting stuff in half, same old thing. Halfway between 0 and 4 pi is 2 pi, and then cut those in half. Halfway between 0 and 2 pi is pi. Halfway between 2 pi and 4 pi is 3 pi. Cut those in half one more time. So we'd have pi over 2. And then we're just counting by half. So 1 half, 2 halves, 3 halves. So 3 pi over 2. 4 halves is 2. 5 halves, 5 pi over 2. 6 halves is 3. 7 halves, 7 pi over 2, and then 8 halves is, sure enough, 4. So we have our scale all set. We know we're working with cosine, and we know we took care of the negative in front of the x with the even identity, so that's literally disappeared because of the symmetry of the graphs. It won't matter. And then what we can know is that we're going to have to move everything to the right, pi over 2, but thankfully that's exactly what one tick mark is. So let's recall that our parent for cosine starts high, dips low, and then ends high within one period, which means we get 2 intercepts within one period. So let's plot these in here. It's just kind of shaping up, putting these basic standard characteristics on the graph. We know it's going to start high. How high? Well, we'll figure that out in a second, but I'm going to put a mark up there just to make sure we get that straight. We're starting high and we're ending high. Well, one full period for us is 2 pi, so I'm going to go out to the end of that first period and put my ending place. I know in the middle, I go low at the bottom, and then I would have my x-intercepts in between. But let's also be consistent in color coordinating. I'm going to put the intercepts as these bright oranges. Everything else, highs or lows, is just solid points, blue points. And that's one full period of this graph. Now, we are going to be shifting everything to the right, pi over 2. So all these points will be moving to the right. I'm going to continue, though, finish out the pattern, so our x-intercepts are every other value. Same thing with the highs and the lows. The pattern just continues. And now let's do our phase shifting. We're going right pi over 2, which means everything's moving one tick mark to the right. All of our points are moving one tick mark to the right. Just carefully mark these on here. And once we have them, of course, you can just visually confirm that it's the pattern you're thinking of, connect them. Let's see, I have one more x-intercept there to move. And there we have it. Okay, if you've kept up with me this long, congratulations. We're almost there, almost done. The only thing more fun to do is go backwards. So for these next couple examples, we're going to do just that. Number 9, this next example says the graph of one complete period of sine or cosine is given. Write the transformation equation for it. In other words, we're going to try to go backwards from the graph to the equation, given that there are some transformations involved, perhaps, right? So notice this graph. It starts at the point 0, 2, so it starts high, starts to dip down, moving to the right. It has an x-intercept at pi over 4. So let's mark this, actually even a similar coordination that we've been doing. X-intercepts are orange. And then there's a low point at pi over 2, next x-intercept at 3 pi over 4, then back up to the top at the point pi comma 2. Okay, so it starts at 0, 2, dips down all the way through the x-axis to pi over 2, negative 2, then back up through the x-axis to pi comma 2. And those characteristics should give us a pretty good idea of what we're working with. And we're saying it's one complete period, or they're telling us it's one complete period given in the picture. That should help us narrow this down and find out what we need. Because in fact, you can tell that from this picture, that distance is pi. The one period is pi. So the period here is pi, which we know should equal 2 pi over b. But we're trying to find b, so we could just solve for it here. And you can cross multiply perhaps to get that. You could say then pi times b, so this implies cross multiplying pi times b. If I cross multiply in this way, to think of algebra on that, then we get pi times b equals 2 pi, which means if you divide by pi on both sides, b equals 2. Okay, so that's a big clue on what's going on here. So b is 2, right? If we're looking at, and by the way, we could assume that this is a cosine graph. You could actually find a way to do it with sine or cosine because they are simply transformations of each other. If you slide one over enough, you get the other one. But we'll just pick on what I would say is the simplest version, which is if you start high like this, we're probably working with a cosine in simplest form. So I'm going to say y equals, and I'll write out the most basic transformation formula first, a times the cosine of b times x minus c. You have the brackets and the parentheses going on, and then plus d. Well, in this case, we figured out that b is 2. From what you can tell on the scale, notice it goes as high as 2 and as low as -2. From that, we could tell that a must be 2. And you could do different, there's variations of what this answer could be. I'm going to leave it without a vertical reflection, which means we'll just keep it as positive 2 for a. So what we could finish is to say that a is 2, so y equals 2 times the cosine of, now in the brackets I'll put the b value of 2. You'll notice we're not accounting for any kind of phase shift, so we'll just say c equals 0, which means we don't do anything else with it. So it'd be like 2 times x minus 0, but the 0 really wouldn't show up, so we'll make that look simpler in a second. And again, there's no movement up or down, so d is also 0. So you could say plus 0, but that gets a little redundant at the end. So you could just say in its simplified form, y equals 2 times the cosine of 2x. That's without those zeros in there, and that should account for it. So we worked backwards, but really using the exact same formulas and processes that we've already been using to go forward. Okay, 2 more. Our next graph starts at the point 0, 0, and then moves upward to a peak of pi comma 3, and then starts snaking back down with an x-intercept at 2 pi, and then down to a minimum, a valley value at 3 pi comma -3. So what we want to do is start the same kind of process here to understand. Well, we're looking at one full period, as they told us, which you can tell from the span. It goes from 0 to 4 pi. So we know the period equals 4 pi, and we know that that equals 2 pi over b. If you want to cross multiply, call it 4 pi over 1 equals 2 pi over b. What would b be? Okay, if you cross multiply, I think you're going to get b equals 1/2. And that's one of the values we need. Notice that we could probably, let's use a positive sign because it's going upward from the origin. It's probably the simplest way to describe it. We'll use this a version of the sine graph. So the amplitude does seem to be affected. It goes as high as 3 and as low as -3. And if we assume it's starting going up, we don't have to use any kind of vertical reflection. So we'll just say here y equals 3 times the sine of, and then remember it's b times x minus c plus d. Well, there's no d, so we'll just say here d equals 0. We'll even say c equals 0 because again, you could say or assume it's not shifted at all. You don't need a shift. So we'll just say b x, so 1/2 x. This is one possible answer. You can find a different phase shift of the same function, or even a version of cosine that could work as well, as long as it's shifted over appropriately, that would match the exact same graph. But this is one option, 3 times the sine of 1/2 x. Okay, let's take a look at our last one. Well, actually, it looks like my picture got cut off here. I'm going to extend this graph just so we have something to work with here. I'll explain it in a second. So this one has a curve that spans into the negative territory. Okay, so we're looking at, in the middle of our graph is the y-axis. Of course, x-axis is running all along. It looks like our scale is such that it probably goes as high as 1/10 and as low as -1/10. It looks like one full period on this one, which was originally cut off. I extended it. If you think about the curvature of this graph, you could say it starts at negative pi over 2, goes up and then down and then back to the same place. So you could call that like one full period. And that distance, all the way from negative pi over 2 to positive pi over 2, would be just one full pi. Which means you could say that's the period. So if our period equals pi, which equals 2 pi over b, then again cross multiply, you would get b equals 2. You can just cross multiply that with pi over 1. B equals 2. So that's part of it. You could say, again, it's hard to say which one you want to use here. I might use a sine value since it's going through the origin, and I might use a negative one since it starts going downward through the origin. So I would say probably y equals negative 1/10, because that's the scale we're looking at here with the amplitude change. And then since b is 2, we could say this is probably sine of, remember it's b times x, but let's be careful here. So it's b times, if we had that factored out, it'd be x minus c plus d. We could say d is 0. And then c, again, you could adjust this to say it does have a phase shift or not. I think we'll go without one, because why, if we don't have to, bother with it? So we could say just 1/10 sine of bx, so 2x. And so really we could leave it just at that. Right? We figured out that b is 2. You could throw a phase shift. Again, there's all kinds of ways you could do other options for this. You could even use cosine. But I think the simplest version here would be just negative 1/10 sine of 2x.